Imagine asking a simple question: how long does it take people in this city to get to work? You ask 12 commuters and get an average of 34 minutes. Tomorrow, you ask 12 different commuters. Now the average is 27. One question, two careful measurements, two answers. Did reality change overnight? Did somebody make a mistake? Or is the changing answer telling us something important? This is the doorway into statistics. Some questions have answers we can reveal exactly. How many chairs are in this room? Count every chair, and you are done. But many questions are too large, too expensive, or too uncertain for that. What fraction of voters supports a candidate? Does a new medicine help patients? Which website design leads to more purchases? We cannot observe every voter, every future patient, or every possible customer. We see a smaller, imperfect window and use it to reason about a larger world. That is a statistical problem. Picture the whole city as an ocean of commute times. Every person is one dot in that ocean. The number we really want is the population average, the center of all those dots. But measuring everyone is unrealistic. So we take a sample, like dipping a cup into the ocean. The sample average is our estimate. Here is the key distinction. The population value is the target. The sample value is a clue. We usually know the clue, not the target. Now dip the cup again. The new sample contains different people, perhaps more train riders, fewer cyclists, one commuter with a 90-minute trip. Its average changes. Dip again, and it changes again. 29, 36, 31, 27. None of these samples has to be dishonest. Variation appears because each sample contains a different slice of the population. A statistic, like a sample average, is not a fixed fact carved in stone. Before we collect the data, it is a moving quantity. If we could repeat this process thousands of times, the estimates would form a distribution, a cloud of possible answers. Most would gather near the true population average. Some would land farther away. This cloud is the hidden object behind a reported number. A poll showing 52% is not just 52. It is one landing point in a range of values the sampling process could have produced. Statistics asks us to see both the dot we observed and the cloud we did not. What makes the cloud narrower? Usually, a larger sample. With only 4 commuters, one extreme trip can pull the average dramatically. With 40, that same trip matters less. With 400, less still. More data does not guarantee perfection. A biased method can collect a mountain of misleading data, but when observations are gathered well, larger samples reduce the random wobble. The answer can still vary, it simply varies less. This is why sample size is not a decoration in the corner of a chart. It controls how steady the answer can be. This leads to a surprisingly useful idea. Uncertainty is not an apology. It is part of the answer. Suppose 2 surveys both report 52% support. Survey A asked 20 people. Survey B asked 2,000. The headline number is identical, but the evidence is not. Survey A should produce a wide cloud. Survey B should produce a narrower one. A margin of error, an interval, or a probability statement describes that difference. It tells us how much movement the data-generating process allows. But changing answers can come from 2 very different sources. Random variation makes estimates wobble around the target. Bias pushes them systematically to one side. If we estimate commute time by asking only people at a downtown subway station, more data may make the result extremely precise and still wrong for the whole city. Random error is about the width of the cloud. Bias is about where the cloud is centered. Good statistical thinking asks about both. A tight cluster around the wrong target is not success. Now notice this pattern in familiar problems. An election poll samples voters and estimates support. A medical trial samples patients and estimates a treatment effect. An A/B test samples website visits and estimates a change in conversion. In every case, a new sample could produce a new answer. That does not make evidence useless. It means we must judge the size of the effect against the amount of expected variation. A small change with a huge cloud is weak evidence. A clear change with a narrow cloud is more convincing. So when you meet a statistical claim, build a four-part map. First, what larger group or process do we care about? That is the population. Second, what hidden quantity are we trying to learn? That is the target. Third, what data did we actually observe and how were they selected? That is the sample and the sampling method. Fourth, how much could the answer change if we repeated the process? That is uncertainty. If one of these pieces is missing, the number is difficult to interpret, no matter how many decimal places it has. A statistical question is not merely a question answered with data. It is a question where we expect variation, and where that variation matters to the conclusion. How long is this one metal rod? That may be measurement. How long are rods produced by this factory? Now we expect a distribution. Which web page won yesterday? That is a result. Which design is likely to perform better for future visitors? Now we are reasoning beyond the observations. The statistical question connects what we saw to what we did not see. So, why does the answer change? Because the data are a sample, and samples vary. The important question is not, why did the number move at all? It is, how much movement should we expect? What might be pushing it, and is the signal larger than the wobble? Once you see that, statistics becomes less mysterious. It is not a machine for producing one perfect number. It is a disciplined way to learn from incomplete, changing evidence, while keeping track of what we still do not know. The moving answer is not the failure of statistics. It is the reason statistics exists.